All right, let's go. Number 10. The pointer state problem. In 1970, Dieter Zeh was a nuclear physicist at Heidelberg working on collective models of the atomic nucleus. The unglamorous business of describing how protons and neutrons move together inside heavy elements. He kept hitting a technical nuisance. His carefully constructed nuclear states refused to stay isolated. They bled into their surroundings. He decided to calculate exactly how badly they bled. Standard quantum mechanics is clear about what should happen. A system in superposition stays in superposition. The wave function evolves smoothly, deterministically, reversibly, according to the Schrödinger equation. Nothing in that equation collapses. Nothing in that equation chooses. Every branch stays alive, forever, with equal mathematical standing. Zeh found that isolation does not exist. Air molecules, stray photons, the cosmic microwave background, everything is measuring everything, continuously, everywhere. He published it in Foundations of Physics in 1970. Almost nobody read it. Wojciech Zurek, then working under John Wheeler, formalized the mechanism in Physical Review D in 1981 and again in 1982, and named it einselection, environment-induced superselection. Eric Juice and Zeh calculated in Zeitschrift for Physik B in 1985 that a dust grain 1/100th of a millimeter across, struck by nothing but ordinary air molecules, loses coherence in roughly 10 to the minus 31 seconds. Serge Haroche's group at the École Normale Supérieure watched the process unfold in a microwave cavity and published the measurement in Physical Review Letters in 1996. The field celebrated. The measurement problem was solved. Then people read the fine print. Decoherence explains why you never see a superposed chair. It does not explain why you see this chair. The density matrix goes diagonal, but a diagonal matrix is a list of possibilities, not a selection among them. Zurek said so himself. John Bell, in a 1990 essay titled Against Measurement, dismissed the whole program as true only for all practical purposes, and practical purposes, he argued, are not physics. Many worlds absorbs the leftover by keeping every branch. But then owes an account of why probabilities follow the Born rule, which remains contested 30 years on. So the most successful mechanism in quantum foundations explains the disappearance of alternatives without explaining the appearance of one. Your entire visual field, right now, is a pointer state whose selection has no accepted physical cause. What picked it? The failure to explain selection has a name, and it is older than decoherence itself. Number 9. The von Neumann cut. John von Neumann was not trying to break physics. In 1932, he was doing housekeeping, putting quantum mechanics on rigorous mathematical footing in his book Mathematische Grundlagen der Quantenmechanik, because the theory had been assembled in 6 chaotic years by people arguing in 3 languages. He wanted axioms. He wanted the thing to be a proper mathematical object. What he found was that quantum mechanics contains 2 rules, not 1. Process 2 is the Schrödinger equation, continuous, deterministic, reversible. Process 1 is measurement, discontinuous, probabilistic, irreversible. They contradict each other. Von Neumann proved that you can slide the boundary between them anywhere, put the cut at the particle, at the detector, at the retina, at the brain, and the predictions do not change. That was meant to be reassuring. It is the opposite. A boundary that can be placed anywhere without consequence is a boundary the theory cannot locate. Physics has an unlocatable line running through it, and nobody knows what it is made of. Every attempt to nail it down has cost something. Bohm's 1952 papers in Physical Review restored determinism with hidden particle trajectories, at the price of explicit. Irreducible non-locality. Gherardi, Rimini, and Weber proposed in Physical Review D in 1986 that wave functions spontaneously localize at a rate of roughly 1 collapse per particle per 100 million years, a real physical mechanism and therefore testable. Underground germanium detector experiments and the LISA Pathfinder spacecraft have since squeezed the allowed parameter space badly without closing it. Everett's 1957 relative state formulation in Reviews of Modern Physics deleted collapse entirely and got branching universes instead. Copenhagen simply declines to say where the cut is, which is not an answer, but a policy. Then, in 2012, Pusey, Barrett, and Rudolph at Imperial College London published a theorem in Nature Physics showing that under mild assumptions, the wave function cannot be mere information about an underlying reality. It has to be real, which means the thing that collapses is a thing. You are on one side of von Neumann's cut. Nobody can tell you which side. One physicist decided the cut isn't a flaw in the theory, but a clue about facts themselves. Number 8. The relative fact. Carlo Rovelli came to this from gravity, not from foundations. Through the early 90s, he was working with Lee Smolin on loop quantum gravity and running headlong into the problem of time. The Wheeler-DeWitt equation, the central equation of canonical quantum gravity, contains no time variable at all. Rovelli spent years trying to understand how a timeless equation could describe a universe that visibly changes. The classical assumption he was working against is simple and almost invisible. Facts are absolute. If a particle has spin up, it has spin up, for everyone, everywhere, full stop. Physics describes a single shared inventory of what is the case. Rovelli's answer was to delete the inventory. In International Journal of Theoretical Physics in 1996, he proposed relational quantum mechanics. Quantum states are not properties of systems, they are properties of relations between systems. A particle has a definite spin relative to the apparatus that measured it, and simultaneously no definite spin relative to anything that hasn't interacted with it. Both descriptions are complete, neither is privileged. There is no view from nowhere. The objections came in waves, and each one made the position stranger rather than weaker. Critics said it collapses into solipsism. Rovelli replied that observers can compare notes, and the comparison is itself an interaction with its own relative outcome. Critics said it smuggles in consciousness. It doesn't, since a photon counts as an observer. Critics said it's just Copenhagen with better manners, but Copenhagen keeps a classical world in reserve. And relational quantum mechanics has none. In 2023, Lawrence Markovich and Yukowski published an argument in Quantum titled Relative Facts Do Not Exist, claiming the framework generates internal contradictions. The debate did not resolve. It metastasized. What survives is a proposal that the word happened has no meaning without a second clause naming who it happened relative to. Your memories of this morning are not records of events. They are records of your interactions with events. If two observers disagree and both are right, what exactly did occur? That question stopped being philosophy in 2018 when someone built the experiment. Number 7. The Wigner's friend contradiction. Daniela Froschiger and Renato Renner were not hunting for paradoxes. Renner's group at ETH Zurich works on quantum information theory, the mathematics behind cryptographic security proofs, the sort of work where you must show that a protocol holds for every possible agent reasoning about every possible scenario. They were checking whether quantum theory can consistently describe agents who themselves use quantum theory. The setup is Eugene Wigner's from a 1961 essay. A friend performs a measurement inside a sealed laboratory. To the friend, an outcome occurred. To Wigner, outside, the entire lab, friend included, remains in superposition. Both descriptions follow from the same equations. The standard reassurance is that this is a bookkeeping curiosity with no observable consequence. Froschiger and Renner proved otherwise. In Nature Communications in 2018, they showed that 4 agents, all reasoning correctly with quantum theory, all applying the theory to each other, will in a fraction of runs derive flatly contradictory statements about a single measured value, not different perspectives. Contradiction. The paper set off a scramble for the flawed assumption, and the scramble is what makes this entry belong here. Some said the friend's memory decoheres and the paradox evaporates, but the proof holds for idealized isolated labs, which are hard, not impossible. Some said agents may not reason about other agents' conclusions, which would break most of science. Some said outcomes are simply relative, which rescues consistency by abandoning shared facts. In 2019, Prietti and Fedrizzi's team at Heriot-Watt encoded the friends as single photons, ran the experiment, and reported in Science Advances a violation of the relevant inequality at more than 5 standard deviations. In 2020, Bong, Tischler, and Wiseman at Griffith University published a stronger no-go theorem in Nature Physics: you may keep locality, or free choice, or the absolute character of observed events. Not all 3. One of those 3 is false. Every version of you that has ever been certain about anything assumed all 3. Which one are you willing to give up? The next result attacks the assumption you probably didn't think was optional. Number 6. The delayed choice. John Wheeler proposed it in 1978 as a teaching device, not a discovery. He wanted a clean way to show students that the wave-particle question is badly posed, so he constructed a thought experiment: send a photon into an interferometer and decide whether to insert the final beam splitter after the photon has already passed the point where it must have chosen to behave as a wave or a particle. Standard reasoning is unambiguous about what should happen. The photon commits at the first beam splitter. Either it takes one path or it takes both. Whatever you do afterwards can reveal that commitment but cannot alter it, because the commitment is already in the past. Wheeler's prediction was that the late choice determines the earlier behavior. He was right. Vincent Jacques, working with Alain Aspect, Philippe Grandier and Jean-Francois Roche at Ens-Cachan, built it and published in Science in 2007. Single photons from a nitrogen vacancy center in Diamond, a 48-meter interferometer, and a quantum random number generator that selected the output configuration while the photon was already in flight, with the choice made outside the light cone of the photon's entry. Interference appeared or vanished according to a decision made after the fact. In 2015, Truscott's group at the Australian National University repeated it with helium-4 atoms and published in Nature Physics. The explanations offered have all been amputations. Retrocausality, the future editing the past, works, but no experiment shows any usable signal traveling backwards. And the correlations only appear after the results are compared. Hidden variables carrying instructions for every future configuration require finely tuned conspiracies. The quantum eraser variant of Kim, Kulik, Shi, and Scully in Physical Review letters in 2000 made this sharper, which path information could be erased after detection, restoring interference in the sorted data. But the raw data never changes. Nothing propagates backwards. The past simply declines to have been definite. Wheeler pointed out the version nobody wants to think about: light from a quasar, lensed by a galaxy, on a path chosen billions of years before Earth existed. What was that photon doing while there was nobody to ask? Wheeler's answer was that the asking is the thing physics is made of. Number 5. The Landauer Ledger. Rolf Landauer was an IBM engineer with a practical problem. In 1961, computers were getting hot, and he wanted to know the hard physical floor on how much heat a computation must produce. The commercial motivation could not have been more mundane. The expectation at the time was that computation was free. Information was regarded as an abstraction, a description laid over physical systems, real in the way a spreadsheet is real, with no thermodynamic weight of its own. Landauer found that erasing information has a price, and the price is set by physics, not engineering. He published it in the IBM Journal of Research and Development in 1961. Erasing 1 bit dissipates at minimum kT ln2 of heat, which at room temperature is about 2.9 times 10 to the minus 21 joules. Not a design limit. A law. In 2012, Siliberto and Lutz measured it directly with a single colloidal particle in an optical trap and published the confirmation in Nature. Information carries entropy. Entropy is thermodynamics. Thermodynamics is physics. Wheeler took this and inverted the whole hierarchy. In a 1989 conference paper in Tokyo, he coined it from bit. Every particle, every field, every space-time interval derives its existence from binary answers to yes or no questions. Matter is downstream of information. The idea kept finding support in unexpected places. Bekenstein showed a black hole's entropy scales with its surface area, not its volume. Ted Jacobson derived the Einstein field equations themselves from thermodynamics in Physical Review Letters in 1995, which means gravity may be a statistical effect rather than a fundamental force. And then the program stalled, for a reason nobody has removed. Information is always information about something, and always for someone. Wheeler never specified who asks the questions. Strip out the questioner and it from bit becomes a metaphor. Leave the questioner in and physics acquires a participant it cannot define. Your body is roughly 10 to the 27th atoms. On this account, none of them are the substrate. They are the answers. Answers to whose questions? Wheeler pushed that question to its limit and produced the strangest proposal of his career. Number 4. The participatory loop. By the late 1970s, Wheeler had spent decades on general relativity and geometric dynamics. He named the black hole. He trained Feynman. He was as establishment as physics gets. What he could not stop worrying about was the initial condition problem. Why did the universe begin with these laws, these constants, this astonishingly low entropy start? The standard framing treats this as a question about the past. Something set the conditions at t=0, and everything since has been consequence. Cause precedes effect, and the beginning is upstream of everything. Wheeler proposed that the universe's beginning is partly downstream of its present. Barrow and Tipler cataloged the idea in their 1986 book, The Anthropic Cosmological Principle, giving it the name the Participatory Anthropic Principle. Observers are necessary to bring the universe into being, because observation is what converts the indefinite past into a definite one. Wheeler drew it as a letter U with an eye at one end looking back at the other. Combine delayed choice with cosmology, and it is not obviously absurd. Quasar photons genuinely do have their histories fixed by present measurements. The demolition attempts were serious, and none of them finished the job. Decoherence explains definiteness without any observer, but leaves the selection problem from number 10 untouched. Critics called it anthropocentric mysticism, then had to reckon with Weinberg's 1987 paper in Physical Review Letters, which used anthropic reasoning to bound the cosmological constant and got the right order of magnitude 11 years before the supernova measurements. The observed value sits near 10 to the minus 122 in Planck units. Multiverse selection removes the need for observers to create anything, but only by asserting an unobservable ensemble. And the circularity never resolves. Observers require a universe. The universe requires observers. You are, on this account, not a late arrival in the story. You are part of what makes it a story. If the loop is real, what happened before it closed? The next entry asks whether laws are even the right kind of thing to be fundamental. Number 3. The constructor inversion. David Deutsch arrived here from quantum computing, which he largely invented. His 1985 paper in Proceedings of the Royal Society A on the Universal Quantum Computer was an attempt to nail down what the Church-Turing principle really claims about physical reality. Working through it, he noticed something odd about the furniture of physics. Information is the central concept of computation, and computation is a physical process. Yet no fundamental law of physics mentions information at all. Physics has run for 3 centuries on one template. Specify initial conditions, apply dynamical laws, predict trajectories. Everything is a consequence of what was there at the start and how it evolves. The laws are the bedrock, and everything else is derived. Deutsch proposed replacing the bedrock with a list of what is impossible. Constructor Theory, published in Synthes in 2013 and developed with Chiara Marletto at Oxford, takes counterfactuals as fundamental, not what happens, but which transformations could happen and which could not. Thermodynamics already works this way. The second law is a statement about impossible tasks. Deutsch and Marletto's 2015 paper in Proceedings of the Royal Society A derived information theoretic structure from constructor theoretic axioms, without assuming quantum mechanics first. The reception has been skeptical for a specific and fair reason. In 13 years, the framework has produced few predictions that ordinary physics does not already make. Critics call it a reformulation wearing revolutionary clothes. The one sharp exception is the gravitationally induced entanglement test, proposed independently by Marletto and Vidral, and by Bose's group at UCL, both in Physical Review Letters in 2017, entangle two masses of around 10 to the minus 14 kilograms through gravity alone, and you would demonstrate that gravity is non-classical. The experiment is at the edge of feasibility and has not yet been done. If Deutsch is right, the deepest truths about you are not what you are made of, but which transformations of you are forbidden. Is a law that describes nothing that happens still a law? The next entry does not reinterpret spacetime. It dissolves it. Number 2. The woven geometry. Brian Swingle was a graduate student at MIT working on condensed matter physics, specifically on entanglement renormalization, a numerical technique Guiffer Vidal had introduced in 2007 for handling strongly correlated electrons on a lattice. It is a computational tool. Its purpose is to make intractable simulations tractable. Swingle was staring at the diagram of one of these tensor networks and noticed that its geometry looked familiar. The assumption he was violating is the oldest one in physics. Space-time is the stage. Fields and particles are the actors. Einstein made the stage bendable in 1915, but it remained the container within which everything else happens, not a thing that anything else builds. Swingle realized the network wasn't like a hyperbolic space. It had the geometry of anti-de Sitter space, the arena of Maldaceno's holographic duality. He published it in Physical Review D in 2012. The supporting structure was already there. Ryu and Takenagi's 2006 paper in Physical Review Letters showed that entanglement entropy in a boundary quantum theory equals the area of a minimal surface in the bulk geometry. Mark van Ramsdonk's 2010 essay in General Relativity and Gravitation took the next step and showed that if you dial the entanglement between two regions of the boundary theory to zero, the bulk spacetime connecting them pinches off and separates. Space stops existing. In 2013, Maldacena and Susskind proposed ER equals EPR in Fortschritte der Physik. Entanglement and wormholes may be the same phenomenon described twice. The obstacle is not subtle, and nobody has cleared it. All of this is rigorous in anti-de Sitter space, which has a negative cosmological constant. Our universe has a positive one, measured at roughly 10 to the minus 52 per square metri. Holography in de Sitter space remains unsolved after 25 years of effort. The most compelling account of where spacetime comes from applies to a universe that is not ours. The distance between your hand and this screen may not be a fact about space. It may be a fact about how strongly two patches of quantum information are correlated. If distance is entanglement, what is left when the entanglement is gone? One physicist argues that what is left is the only thing that was ever really there. Number 1. The mathematical substrate. Max Tegmark was a working cosmologist, power spectra, microwave background data, the grinding statistical labor of extracting parameters from noisy sky maps. The question that pulled him sideways was one of bookkeeping. If you wrote down a genuinely complete description of the universe, what would be left in it? The standard view, which almost nobody examines, is that mathematics is a language. Reality is made of stuff, and equations describe the stuff. The map is not the territory. Eugene Wigner had already flagged the discomfort in 1960 in his essay on the unreasonable effectiveness of mathematics in the natural sciences, and then left it flagged. Tegmark's answer was that the description, stripped of every human word, contains no stuff at all. He argued it first in Annals of Physics in 1998 and fully in Foundations of Physics in 2008 under the title The Mathematical Universe. The claim is that a complete description must be free of what he calls baggage, every term that requires a human to explain it. What survives is pure mathematical structure, relations, symmetries, sets, and a description that is identical in every respect to the thing described, he argues, is not a description. Every mathematical structure that can exist does, and observers find themselves inside the ones that support observers. The counterattacks are real, and none of them is fatal. Gödel's incompleteness theorems mean most mathematical structures contain undecidable truths, which force Tegmark to retreat to a computable universe restriction that discards most of the ensemble. The measure problem is worse. With infinitely many structures, no one knows how to define probabilities, so the theory predicts nothing specific. Jürgen Schmidhuber's 1997 algorithmic proposal weights structures by program length and gets different answers. And the standing objection is that unfalsifiable claims are not physics. But the alternative is to explain what physical existence adds to a structure that already has every property that structure has. You have never encountered stuff. You have encountered structure, relations between quantities, holding stably enough to feel like a floor. What would it feel like from the inside to be a theorem? 10 entries, and not one of them sits at the frontier of physics. Every single one lives at the center, in measurement, in thermodynamics, in the field equations, in the arithmetic of information. These are not gaps at the edge of the map. They are cracks running under the load-bearing walls. The universe is not confused about what it is. It has been consistent and precise and utterly indifferent for 13.8 billion years. We are the ones holding a description that keeps working while refusing to say what it is describing. If you want to see more videos like this, click the video on screen now.